So, continuation for the introduction. Oh, I thought that I'm using this. I'm trying to use the presentation itself rather than that small shape. Yes, here we go. So, in some applications, you might need to utilize the solar energy as much as you can. What we have been seeing previously was assuming that you have a solar collector which is fixed in location, in its orientation is fixed, does not change. And then we are looking for what is the best or best position that it would be to gain the maximum amount of energy all over the year, which means that we can have more energy than needed in summer, less energy than needed in winter, and same energy as a standard forms in the spring and autumn equinox. Sometimes you need to design your system so that you can use as much input of the sun as possible. But the sun location with respect to the earth is not fixed. I mean, from the perspective of somebody sitting on the earth, he would tell you that the sun is going to rise in the east and then it's going to set in the west. And the location changes with the hours of the day. If I need to use maximum amount of solar energy, then I need to do what is called tracking, which means that I would make my surface move so that it follows the sun. And the motion here can be done simply using one axis. So it can move over an axis which is basically extending from the directions of east-west direction, or axis in the north-south direction, and so on, or parallel to the Earth's axis. So it can be an axis which changes direction or changes in one direction. Or you can do it for a double axis, which means that not only going in one dimension, but it's moving in two dimensions so that it can more accurately follow the sun. What's the benefit? The benefit is that we get more and more energy, because whenever there's a motion of the sun with respect to the earth, again, from the perspective of somebody who is on the earth, then you are following the sun exactly. And this can be done either manually, or sometimes it is done through controls like computer programs that are written and connected to motors. And the motors are moving continuously, minute by minute, so that the sun is in the focal of your collectors, and you are getting as much energy as needed. There's a couple of problems here. Not really problems, but the consequences. Number one, tracking systems are going to be much more expensive. So you need not only the solar collectors, but you need also a mechanism which needs a lot of elements and this kind of pivots and motors. So it's basically it's a substantial addition to the price. That's number one. Number two, that this amount of or this kind of systems need energy to move. We are talking about motors. And if you are talking about a PV system, you may use that part of the energy you are generating to run the PV. So at the end, is it worth like using part of the energy to run your system, or put the system without this additional penalty of energy that from what you generated, and you just keep, or it would be enough what you get from the solar rays or solar radiation in a fixed location? There's no one answer to this. It depends on your application. If you are looking for application for heating a house, it's not a big deal. I mean, you can make it fixed. But if you are looking for an application, for example, where you need to generate power, a large amount of power in a big solar power plant, then you may need to consider the issue of rotation. Whether it is single or double axis rotation, again, it depends on your case. So that's something, the answers is not general. It is something that is going to depend on the case that you have in hand and you see, does it deserve the hassle of adding a system to track the sun or not? Here, this part of that chapter is dealing with this specific issue of what if we are thinking of tracking the sun. So some solar collectors would track the sun, like the solar collector orientation changes. It's not fixed as we used to see. And it is moving in a prescribed, in a designed way to always to minimize the angle of incidence of beam radiation on the surface and then maximize the incident beam radiation. The angle of incidence and the surface azimuthal angle are needed for these collectors. You need to know them and specify them and see how they are going to change. The relationships in this section are going to be useful in case of radiation calculations for the moving surfaces. A lot of work have been done with this again, and the work is dated back since 1953 onward. The tracking systems are classified whether they are a single axis tracking, like as I mentioned, whether it is going through or moving with respect to a horizontal east-west axis or a horizontal north-south axis, a vertical axis, or parallel axis to the Earth's rotation axis. So it depends on what is it that you want as a single axis, or if you need a two-axis system there, or a system which is being tracked by moving in two directions. We have a set of equations that are providing that kind of information for the parallel axis. And here the kind of interesting argument which is given by this figure is it is showing extraterrestrial radiation. Extraterrestrial, again, this is the solar radiation which is coming before it enters to the atmosphere, before it gets disturbed or attenuated due to the existence of sand particles or clouds or water vapor, whatever. So this is the origin which is coming, or the total quantity which is getting before hitting the Earth. It's coming on a first surface with a slope which is equal to the latitude, and surfaces that track the sun about a horizontal north, south, or east-west axis at a latitude of 45 at a summer or winter solstice. And what you can see here in this figure, there is NS, which is north, south. There is EW, which is the east-west, and there is fixed values. So again, the point, and it is meaning something for summer, something for winter. So the line here, the solid line, is the line which is showing the radiation falling into a constant surface. This surface is tilted 45 degrees. And this is the amount of solar radiation, which is limited between 6 o'clock in the morning and 6 o'clock in the evening. And it's fixed. So there is little radiation in the morning. It comes into a peak around noon, and then it falls back again until the sun sets at 6 o'clock. This is versus another system which is tracking the sun in the north-south axis. So you set an axis which is directions from north and south, and then it is rotating across this axis. And what if it's an east-west direction? So this is for the summer direction. For the winter, that black line here is for the fixed collector, and then the dashed lines are for both east-west and north-south. Now this will tell you that when you are thinking of a tracking system, you are not putting it only for summer. If it's only for summer, I would tell you put it at northwest direction. It's going to give you a total amount of energy which is high. But look at the north-south direction here in winter. It is quite less. So this is important. And some of the applications that even people were talking about that in some videos that are on the net. The application is a controlling factor here. Because if you need a system that's going to provide solar collectors for heating of school. School time is basically in the winter. So the winter is more important to you because the school is not on summer. Accordingly, you may need to look at what is going to give you the maximum amount of radiation in winter. And in winter, it can be a system which is tracking the sun on east-west direction if your economics or if your budget are going to afford it. Otherwise, a fixed system could be good enough. But you will not go for a north-south axis in winter because it is given the minimum radiation. In summer, if you have an application that only runs in summer, like for example, you need heating for a swimming pool, and the swimming pool is so large that you decided to, you normally don't need no heating in summer, but you can have an application where you need more solar energy. Say that you need to put PV panels to run air conditioners. Then probably you have your system which is situated to provide the north south axis, and your collector is going to move around the north south axis. That's going to provide you with more energy that can run your PV system in summer to run your air conditioners or more air conditioners due to high energy there. So the point here, it depends really on what is your application. If it's all year round application, then you will probably need to consider the one which is fixed. Unless you are talking about another system which is more sophisticated to allow you to use a two tracking systems, for example, or like, I mean, tracking over two axes. So that was basically the kind of argument that this part has been built on. So tracking can significantly change the time duration of the incident beam radiation. You are following the sun and you are getting the maximum amount of energy at all times. But depending on your application, we have seen in the figure that you can get better results in one season, but lower results in another season. And then it depends on your application. The differences actually, or the differences that are there, there's something that has not been taken into consideration, which is in case of clouds or atmospheric transmission. So the values that you are going to get on the ground are going to be a little bit less compared to what we have seen in the figure. For a plane rotated about a horizontal east-west axis with a single daily adjustment, that's another issue. That are you going to have it on the axis and change the adjustment every day? Because as the days pass, the value of delta changes, and then you keep on changing that. Based on that, the cosine theta, which is the angle of incidence, can be given by that expression. The slope of the figure is going to be fixed in every day, which is this. The surface of the azimuth angle of a day will be 0 to 80, depending on the latitude and the declination. We said that it's something which is fixed north to south direction. So the angle is going to be either 0 or 180, depending on where you are. Are you on the top part of the atmosphere, lower part of the atmosphere, depending, of the Earth? What about a plane which is located on or rotating around an east-west axis? Then the cosine theta is going to be given by this value, and that would be the inclination beta, and then the value of gamma is going to be given here. So now these are again some sort of special cases that you're going to refer to based in your system. So if your system is located and rotating around an axis which is basically extending in the north south direction, you are going to use these equations here, 171 A, B, C. If your system is rotating around an axis which is extending east-west direction, then 172 A, B, C are the equations that you are going to use. If your system is located at north-south axis, but with continuous adjustment, which means that you are adjusting it something like you are put into a program where that changes within the day. You are not fixed it the whole day, but you are changing it within the day. Then the values of the incident angle are going to be calculated according to the group of equations, which is given as 1 7.3, A, B, and C. If you are going to have like a vertical axis, then this is going to be, and the book has a little bit more than that. It tells you what if it's a horizontal axis, east-west, with continuous tracking or continuous adjustment, not a single day adjustment. And again, the difference is a single day adjustment throughout the whole day. There's no adjustment except that it moves around this axis. But if it needs further adjustment, then you are going to call it a continuous kind of adjustment. And these equations are providing us with this type of expression for the cosine theta, which is the angle of incidence for these applications. So previously, in the previous classes, we're talking about the issue of the angle of incidence based on the case that we have a fixed position of our collectors or surfaces. Today, we are now looking at different cases in which we have tracking, and the tracking is being done with respect to several axes, whether it is north, south, east, west, whether it is fixed for a day or changing during the day, or the case where we have a vertical axis, which is represented here as well. An example is given here, which is nothing but a direct substitution to the equations that we had earlier in the previous slides. This is talking about asking for the angle of incidence of beam radiation, slope of the surface, azimuth angle for the surface at an altitude of 40 degrees, inclination of 21 or declination of 21, and for an hour angle of 30 at 2 p.m. versus another condition where for the same altitude, for the same value of delta, but the value of omega has changed. And changing the value of omega, definitely means that we are changing the hour in the day. And this is all if it's continuously rotated about x-axis, about east-west axis to minimize theta. So here it has specified from the last statement in that example, which set of equations we have to. You have to look for the equations that are dealing with rotation around east-west axis for continuous rotation. And based on that, you are going to look for equation 172, A, B, and C, and then you put these equations and substitute directly into them so that you can get the value of theta. You can get the value of theta z, the zenith angle, and then you can get the value of gamma s, which is the solar azimuth. And finally, what is the, at that hour of the day, what is the value of beta, which is the inclination to the, or tilting to the horizontal. The other case is going to be, again, which is the second one for omega is equal to 100, then you substitute and get the same values here, theta, theta z, gamma s, and beta. So that was the thing here. What we have is some sort of, again, direct substitutions, but we have to identify which set of equations that we need to use for the angle of incidence, for the zenith angle, for the solar azimuth, and for the tilt angle. We're just left with maybe less 1 minute. So I'm going to stop here, and then again, you will need to do not pile. So that's something I would urge you a lot to do, I mean, very much to do. Do not pile the material. Do not say that I'm going to wait until we finish, for example, chapter 1, and then start reading it. This chapter in particular is laying the foundation in terms of orientations and angles. So I would urge you to read it. I wouldn't say every day, but every other day. Try to resolve the examples that are given in the book. This is, or the examples that are given here if you have not yet received the book. Try to read them again, solve the game by your hand, because this is the way you are going to get more comfortable dealing with the angles. And that's important at the moment, because we are going to rely on these angles for the rest of the course. We said that we have the first 6 chapters are some sort of preparations. into chapter number 6, which is talking about our application of flat plate collectors. So when we talk about flat plate collectors, we are not going to explain again what orientation should the flat collector be done, because we have already done that in chapter 1. So try to be prepared with this background before we get into the applications of this information when it comes to chapter 6 onward. So that would be it for today. I would stop here and then we'll continue the rest of this chapter in our next class, inshallah, on Wednesday.